Well, now let's see how this idea of divergence relates to some of the ideas that we've talked about in the previous sections. So here I'm just going to talk through a little bit of a recall. And we're actually going to go all the way back here to the idea of Green's theorem. Green's theorem was a really cool idea that related the ideas of a line integral of a vector field over a closed curve in 2 space to a double integral over the region enclosed by the curve. So you might recall that we said that we had back in Green's theorem that if there was some sort of a curve existing in space with positive orientation, instead of trying to calculate the line integral for like our f dot dr, we could instead compute a double integral of some stuff over the enclosed space of D. That was the concept, that we could substitute out one integral for this double integral. Instead of doing something with the boundary of the curve, or the boundary of this region, we can instead integrate over the region itself. So what we want to see here is that there are actually two very interesting ways that we could think about generalizing Green's theorem. Take a look at the first one here. We might be interested in trying to increase the dimensions of the integrals. So like here I have a single integral and a double integral. But maybe I could increase those to a double and a triple. Now, more precisely, we might guess that if I was to say that the flux of a vector field, as opposed to like the work for a vector field, through a closed surface, as opposed to a closed curve, might be equal to a triple integral, as opposed to a double, taken over the region enclosed by the surface. So again, we've been dealing in the last section with saying like, suppose that I had some sort of a solid, right? So we dealt with something like a sphere, and we said, I want to know about fluid flow that happens coming in and out of this sphere. And so maybe it's the case that this relates to something kind of like a line integral, in that this had an orientation and my surfaces had orientations. And since this was a closed curve, here I have a closed surface. And instead of computing the single integral, and instead of here of computing the double integral for the flux, maybe I could instead just deal with integrating what was enclosed. That is, I do this double integral over what was enclosed. And so maybe here I can do a triple integral over the region or the solid that's enclosed by the surface. So that seems like a kind of interesting connection. There seems to be some related ideas here. Well, another thing that we could think about is, again, Green's theorem dealt with a closed curve existing specifically in 2 space. But couldn't I have a closed curve in 3 space? Like you could imagine right now just waving your finger around the room in a closed sort of a pattern, like draw a curve out in the air. And it exists in 3 space. It has height and depth and width, like in terms of where those points go. And so I might guess that then if I had a curve that existed out in 3 space, maybe it, does something, wow, kind of like this, but it's a 3 space curve. Well, I could maybe still imagine orienting it. It's just it's in 3 space as opposed to in 2 space. But that would mean that I don't just have like a 2D region enclosed here, but this is like a 3D surface. And so maybe it's the case that I could go ahead and say that the line integral over the vector field as I move along this 3 space curve could be equal to maybe like a surface integral over this 3D surface, as opposed to just this double integral over this flat surface. So this first idea, this idea number 1, is the idea that we're going to focus on in the rest of this section. It leads us to what we call the divergence theorem, the focus of what we're doing in this section. And the second generalization is going to actually be what we talk about in section 5.8. Now for the sake of time in this video, and I'm going to go ahead and actually skip some of the justification here for the theorem that we're going to get to with the divergence theorem. Of course, if you're interested, please feel free to go ahead and read through the notes that are in Blackboard and ask me as many questions as you would like via email or during office hour time. But I'm going to go ahead and just jump here right to what the divergence theorem says, and we're going to see this kind of generalization of Green's theorem. So again, I'm just going to go ahead and up above here I'm going to recap one final time what Green's theorem told us, because it's really important to see this connection. So Green's theorem said that if I had a positively oriented curve, C, and I was going to go ahead and try to compute a work integral as I moved around C, this closed curve. That would instead be equal to a double integral over the region of D, which was the region that was enclosed. So notice the similarities here. Everything's just going to be brought up a level in terms of dimension. So how about we let G be a solid? So G here is kind of like an upgraded version of D. It's not an area, but it's a solid. And the surface of that solid is sigma. So sigma is kind of like C. And let's say that this is oriented outward. So there's an orientation on that surface. Just like here there was an orientation on the C. Well, if F is a vector field whose component functions have continuous partial derivatives, then on an open region that contains, they have continuous partial derivatives on an open region that contain G. And if n is an outward unit normal on sigma, then I can state the following. So if I wanted to compute the flux through the flux of my vector field through my surface of sigma, again, this is similar to kind of like this line integral that I have here. Notice I'm working through the surface that has an orientation, and I kind of have this work integral sort of set up. It's a flux integral. And then we can say that's actually going to be equal to a triple integral over G. Again, G is like the D. It's the region that's enclosed by that closed surface. So a triple integral over G, and the fancy function that we're going to use is the divergence of F. So this is a connection between a flux integral and a triple integral that we're going to have here. Now, as I state down here in this note, the divergence theorem says that the flux across the boundary of G is the same as a triple integral over G. The theme to Green's theorem and the divergence theorem is that there's some integral over a region is equal to another integral taken over the boundary of the region. In fact, this even relates back further to ideas of fundamental theorem of calculus, even all the way back in Calc 1, where we saw that there was a connection between a specific integral and that we could instead kind of look at the boundary of what we were integrating over, and just for a very special select function, we could kind of work with that function evaluated at some endpoints. That is, the edges or the boundaries of our interval. So here, C acts as, again, that boundary of the D, and here sigma acts as that boundary of the G. So we kind of have this big connection here, similar sorts of ideas. Now, we're going to go ahead and in the next video see how we can start to apply this to some specific examples. What this will actually serve as is a shortcut to actually go ahead and compute either a triple integral and taking this theorem and starting on the right side and going to the left, or a shortcut for computing a flux integral starting on the left side and easily going to the right.